In this module, we will study what are the application of differential equation. A differential equation is a mathematical equation that relates some functions with its derivatives. In applications, the functions usually represent physical quantities, the derivatives represent their rate of change, and the equation defines a relationship between the two. Because such relations are extremely common, differential equations play a prominent role in many disciplines including engineering, physics, economics and biology. In pure mathematics, differential equations are studied from several different perspectives, mostly concerned with their solutions, the set of functions that satisfy the equation. Only the simplest differential equations are solvable by explicit formulas. However, some properties of solutions of a given differential equation may be determined without finding their exact form. If a self-contained formula for the solution is not available, then the solution may be numerically approximated using computers. The theory of dynamical systems puts emphasis on qualitative analysis of systems described by differential equations, while many numerical methods have been developed to determine solutions with a given degree of accuracy. In the last module, we have studied about the differential equation and how solutions are achieved. Differential equation or differential can be used to analyze the dynamic equilibrium, Solow growth model, population growth, exponential decay, falling object. After studying this module, you shall be able to know how differential equations can be used to analyze growth model, understand the application of differential equation for the population growth, understand the application of differential equation for dynamic equilibrium. Let us start this module with dynamic equilibrium. Differential equation can be used to trace the time path of the price movement to the equilibrium, and from the equilibrium price, that is convergence or divergence in the demand supply model with respect to time. As we know that change in price is directly proportional to the excess demand and inversely proportional to excess supply. This can be explained as follows. dP by dt is equals to Z into Qd minus Qs. In this equation, dP by dt is the change in the price with respect to time. Z is positive constant. Qd is quantity demanded. Qs is quantity supplied. Equation states that if Qd is equals to Qs, then dP by dt is equals to 0. Let the demand function be Qd is equals to A minus Bp, where A and B are greater than 0. Supply function B, Qs is equals to C plus dP, where C and D are greater than 0. Equation can be written as dP by dt plus Z into B plus D into P is equals to Z into A minus C. Equation is form of differential equation and coefficient of price is different from 0. Solution of previous equation can be written as Pt is equals to P naught minus P star into e to the power minus kt plus P star. Equation states that as t tends to infinity, price moves towards the equilibrium price and equilibrium price is dynamically stable. Now, we will discuss Solow growth model. The neoclassical model was an extension to 1946 Harrod-Domar model that included a new term, productivity growth. Important contributions to the model came from the work done by Solow and by Swan in 1956, who independently developed relatively simple growth models. Solow's model fitted available data on US economic growth with some success. In 1987, Solow was awarded the Nobel Prize in Economics for his work. Today, economists use Solow's source of growth accounting to estimate the separate effects on economic growth of technological change, capital and labor. The Solow-Swan model is an exogenous growth model, an economic model of long-run economic growth set within the framework of neoclassical economics. It attempts to explain long-run economic growth by looking at capital accumulation, labor or population growth and increase in productivity, commonly referred to as technological progress. At its core, it is a neoclassical aggregate production function, usually of a Cobb-Douglas type, which enables the model to make contact with microeconomics. The model was developed independently by Robert Solow and Trevor Swan in 1956 and superseded the post-Keynesian Harrod-Domar model. Due to its particularly attractive mathematical characteristics, Solow-Swan proved to be a convenient starting point for various extensions. For instance, in 1965, David Cass and Jalling Koopmans, I repeat, and Jalling Koopmans integrated Frank Ramsey's analysis of consumers' optimization, thereby endogenizing the savings rate. See the Ramsey-Cass-Koopmans model. Solow growth model try to explain long-term growth of an economy. It explains how the changes in capital stock, change in labor force and change in the technology affect the long-term growth of an economy. Moving on to the assumptions of the model, production function exhibit constant returns to scale and diminishing return to factor, that is y is equals to f k comma l. Dividing both sides of the equation by L, y by L is equals to f k by L comma 1. Equation can be written as y is equals to f k, where y is equals to y by L and k is equals to k by L. Here both y and k are in small case letter. Rate of depreciation is constant. Rate of population growth is constant. Rate of saving is also constant. According to this model, some proportion of output is saved and get invested, and capital stock of an economy depends upon the rate of savings, that is S. K is equals to Sy. Let A be the rate of depreciation, then total depreciation will be AK. Change in capital stock is investment minus depreciation. That is dk is equals to 1 minus ak and dk is equals to sy minus ak. Equation is differential equation. The Solow model is remarkable in its simplicity. Looking at it today, one may fail to appreciate how much of an intellectual breakthrough it was. Before the advent of the Solow growth model, the most common approach to economic growth built on the model developed by Roy Harrod and F.C. Domar. The Harrod-Domar model emphasized potential dysfunctional aspects of economic growth. For example, how economic growth could go hand in hand with increasing unemployment. The Solow model demonstrated why the Harrod-Domar model was not an attractive place to start. At the center of the Solow growth model, distinguishing it from the Harrod-Domar model, is the neoclassical aggregate production function. Now, we will discuss the population growth or exponential growth. Let Pt be the quantity that increases with the time t, and the rate of increase is proportional to the same quantity P as follows. dP by dt is equals to Kp, where dP by dt is the first derivative of P, K, which is greater than 0, and t is time. The solution to the first order differential equation is given as follows. Pt is equals to a into e to the power kt, where a is constant not equals to 0. If p is equals to p naught at t is equals to 0, then p naught is equals to a into e to the power 0, which gives a is equals to p naught. The final form of solution is given by pt is equals to p naught into e to the power kt, assuming p naught is positive, and since k is positive, pt is increasing exponential. Now we will discuss the exponential decay. Let mt be the amount of a product that decreases with time t, and the rate of decrease is proportional to m as follows. dm by dt is equals to minus km, where dm by dt is first derivative of m, k, which is greater than 0, and t is the time. After solving the first order differential equation, we obtain mt is equals to a into e to the power minus kt, which shows it decreasing exponentially. Next, we will discuss the falling object. Suppose an object is dropped from a height of ht at time t. Let bt is acceleration and zt is velocity. The relationship between h, b and z are as follows. bt is equals to dz by dt, zt is equals to dh by dt. For falling object, bt is constant and is equal to g, which is equals to minus 0.98 meter per second. Combining the above differential equation, we can obtain the following equation. Capital D square h by dt square is equals to g. Integrating both sides of the equation, we obtain capital dh by dt is equals to gt plus z naught. Integrating again, we get ht is equals to 1 by 2 into gt square plus z naught t plus h naught. Above equation states that the height of an falling object from initial height h naught at velocity z as a function of time. Apart from the above application of differential equation, it can also be used at various economic applications. Let us now summarize what we have learnt in this module. Differential equation can be used to trace the time path of the price movement to the equilibrium, and from the equilibrium price, that is convergence or divergence in the demand supply model with respect to time. Pt is equals to P naught minus P star into E minus Kt plus P star. Solo growth model explains how the change in capital stock, change in labor force and change in technology affect the long-term growth of an economy. Pt is equals to P naught into E into Kt, that is population growth, where P naught is positive, and since K is positive, Pt is increasing exponential. Ht is equals to 1 by 2 into Gt2 plus z naught t plus h naught states that the height of an falling object from initial height h naught at velocity z as a function of time.